Yeah, you can talk. You're gonna end up on YouTube, but you can talk.
I'll be YouTube famous.
You'll be YouTube famous? That's JT Garcia.
We should like make you an
Now
intro.
YouTube famous.
YouTube famous for ASMR.
Oh, that's okay. All right, so one more time. Why are we learning about electromagnetic radiation in chemistry?
Study the structure of the atom.
To study the structure of the atom,
Yes.
especially the electrons. Okay, so here's the deal. All energy moves in waves. Okay. There's actually two kinds of waves. One kind of wave is called a longitudinal wave, and it looks like a slinky. Those are the kinds of waves that sound uses to travel. Now, the deal with longitudinal waves is that they need matter to travel through. They have to have atoms in order for that wave to continue moving. They have to move through atoms. So like the sound is moving through the air right now, right? It's moving through the atoms in the air right now. And sound will move through water, correct? It sounds weird, but you can hear underwater, right? And if somebody's really loud, you can hear the sound travel through the wall. Okay, so that type of radiation or energy travels in these kinds of waves. Light and other types of energy associated with light move in something called transverse waves. And any kind of energy that moves in a transverse wave is known as electromagnetic radiation. So light is a form of electromagnetic radiation. The cool thing about this is that transverse waves do not need matter to move through. Light can go from the sun to the earth, right? Is there anything in between us? Just empty space, right?
I mean, skin cancer.
Skin cancer? The radiation, ultraviolet radiation, UV light, has a higher frequency, more energy than regular light. So if you look at all of the different types of electromagnetic radiation, UV light has a lot of energy. And so it's just so much energy that it starts to mutate the cells in your skin. Yeah, it's not mutant like Teenage Mutant Ninja Turtles or like really cool superheroes like...
X-Men.
Yeah, you won't become an X-Man. You just get cancer and die. It's really not as cool as the movies make it sound.
What about the kid? The kid that got struck by lightning?
Kid that got, I don't know, what happened to
The
him?
kid that got struck by lightning. He said he's waiting for his superpower.
Oh, he's not gonna get him. I'm pretty sure all that kid got was a heart attack.
He was alright.
Your heart stops when you get electrocuted with that much, yeah. So he did live. I think he lived, right? You get burned by all the energy, then.
Oh, I heard you get like a cool, like, kind of
So I guess that scar could be a superpower?
Yes, see?
Oh yeah, you did.
It looks
Yes.
like lightning.
He got caught.
Yeah. All right, so here we go. Transverse waves carry electromagnetic radiation. They do not need any matter to move through. That's why the light from the sun can go to the earth. Also, the UV light from the sun can go to the earth. Transverse waves have a couple parts. First is the crest. That's the top. Bottom is the trough. You know, just like a trough for animals. Yeah. The distance from crest to crest or trough to trough is a single wave. And we can measure the length of a wave. It's called wavelength. It's measured in meters because that's metric. Now, since a lot of waves actually are very small, like light waves are really small, sometimes they're measured in nanometers instead of meters. However, in all of your calculations that you guys do, it has to be in meters. So, I'm going to put this conversion here. 1 meter is equal to 1 times 10 to the power of 9 nanometers. So if you need to convert meters to nanometers or vice versa, there's the conversion for you right there. But all of your calculations have to be done with the wavelength in units of meters.
I said so slow down.
There's going to be a little dimensional analysis, yeah.
Oh yeah, that's
There it is. Okay, so frequency is the number of waves that pass a certain point each second. Okay, so number of waves per second. Now, sometimes they leave the waves part out, and it'll just be in units of 1 over seconds, or seconds to the power of -1, because that's the same thing as 1 over seconds, yeah? Or sometimes they'll call it hertz, HZ. You might have heard of hertz. You guys heard of hertz before? Or megahertz, right? Yeah, they usually measure like your frequency on your radio in megahertz, okay? All right, so then the next thing, velocity. So every wave has a speed. The nice thing is that that speed is the same for all kinds of waves, and it's equal to the speed of light, and it's 3.00 times 10 to the power of 8 meters per second. See how the unit is meters? You got to use meters in all the calculations, because the speed of light is given in meters per second. So microwaves from your microwave, and radio waves, and light waves, and, you know, Hulk building X-rays. Actually, Hulk wouldn't have superpowers either. Those would be tumors. But, so all of that would have the same speed. There it is. That's the speed of light. And in any calculation, anywhere you see the letter C, you drop that number in. Does that make sense? Okay.
Why do microwaves explode when you put aluminum?
When you put the metal in there?
Element.
I don't know. It has to do with the way that the energy bounces off of the metals. Like it's absorbed by, the energy in a microwave is absorbed by water, but not by other materials. So like you'll notice plastics don't really get hot in the microwave. The energy just kind of is around them, but the metals conduct the electricity, I think. And so it starts to like bounce around in there and eventually build, and it blows stuff up.
Yeah, because
I'm sure you can find somebody who explains it more scientifically than I do, but
I put something in the microwave and I didn't realize it had aluminum in it, and it's like,
Oh, I've blown up too on my
like,
first
you can see, you know, it left burn marks everywhere.
oh God.
And
There was
blow
like
up,
lightning
but
inside
that's
of my microwave.
Yeah, it does. It looks like lightning in the
Yeah,
microwave.
I was like,
Yeah, you know what? I blew up a microwave when I was a kid too. My ID badge for school, I washed it one time and then it started to grow mold. So,
your solution was to microwave.
well, I asked my science teacher, I was like, how do I get rid of this mold? And she said, oh, that's easy. You can kill it if you microwave it. Well, she didn't specifically say to take the clip off. So, like, I just tossed it in the microwave and then blew up my microwave. It was great. It actually wasn't the whole microwave. It was just, you know, like that glass plate.
Yeah.
That shattered. And then there was a nice little scorch mark on the bottom of the microwave. But my parents were like, it's still usable. Always.
Yeah, no, nothing's.
I've also,
sits
like-
there and gets like super scorching hot on one side.
Yeah, you just have to stop it every once in a while and turn the bowl around. Yeah, and then.
Yeah.
You know.
I've also like
all right.
caught my toaster on fire, but like.
Oh, no.
that's a different story.
Oh, toaster's great.
You actually
Shield bag in the microwave.
No, I didn't put a fork in the toaster. It just kind of caught on fire.
Yeah, well, it catch on fire with like electrocuted.
I think that'll like electrocute
Put a
you.
fork in it,
It can electrocute you, yeah.
like death.
Because I've seen like people stick stuff in there. and
Pretty
it's,
sure
like,
it's bad.
Like
I
an
stuck
microwave.
I stuck a fork in a toaster the other day. It didn't shock me.
Was it?
Yeah.
Was
Was it plastic?
I realized after I'd done it what I had done.
I think the newer toasters,
Yeah, it's
like
stuck a fork.
I don't know how it works. I know they definitely don't go in the bathtub.
What,
Okay.
toasters?
Here we go.
Oh, yeah.
life hack. You can save so much time.
Yeah, no.
That's
Okay.
the way to do it.
All right, so listen, guys.
Fit, not live.
Waves of energy travel in pieces. So it's not like one continuous wave, okay? The waves are actually broken up, and those little parts are called photons. So instead of one big continuous wave, it's like little packets, little photons, okay? Now those photons cannot be broken into smaller pieces. Only certain amounts exist.
You can have one.
So the way that I think about this is it's almost like money, right? Like you could take $1 and you could break it into 4 quarters, correct? And you could take the quarters and you could get 5 nickels out of each one. Okay. But you'll never have a 30-cent coin, will you? And there's no such thing as a 2-cent penny, right? Only certain coins exist. Only certain bills exist when you have money. And so it's the same way with energy. There's only certain amounts of energy that are available as photons. Does that make sense to everybody? Okay. So only certain quantities of energy exist. And another way to say that is to say that energy is quantized. So a lot of time, this is called quantum theory, because we're talking about the energy that's traveling around in photons, the certain amounts of energy that's available as photons. Okay? So don't be afraid of the word quantum theory. We're just talking about how much energy is in photons. Okay? And we can calculate that energy. So that's capital E. That's the energy of a photon. So anytime you're calculating E, that's what you're calculating. Okay? You guys have used these equations before. So the first one is E is equal to the product of Planck's constant times frequency.
Oh, this one is fun.
No, it's really not. So Planck's constant is just a number, and it's equal to 6.26,
Yeah, we used it last year.
yeah, times 10 to the negative 34th power. Okay, so that's Planck's constant. We also used a different
That's a very
equation
small,
last year.
That's a very small number.
It's super small, yeah. We also used another value. We did C is equal to wavelength times frequency, right? Do you guys remember that equation right there? We used it a lot. Now, if I solve for frequency, if I do some algebra, if I divide both sides by wavelength, won't that give me frequency?
Yes.
So C divided by wavelength equals frequency. And if all I do is use this in the equation instead of F, I get this equation right here. Do y'all see that? So this is just another way to calculate energy, but instead of using frequency, I'm using wavelength. Speed of light. So again, that's just a number you drop in the equation. It's at 3.00 times 10 to the 8th. Okay? I'm right. Okay, so those are a few equations that you may have to use. And then this question, this is a good one. Do photons have mass? So they were trying to figure out how much mass is in energy, which you might think that none, right? But here's the deal. We have this equation using Planck's constant. So thank you, Max Planck, for that one. And then we have this equation right here. Does that look familiar? E equals mc squared. That's Einstein's, right? Einstein. So listen, if E is equal to HF and E is equal to mc squared, then I guess I can set HF equal to mc squared. You see what I just did there? Transitive property. And then if I want to solve for mass, wouldn't I divide both sides by c squared? So HF divided by c squared gives me the mass of a single photon. So if you ever needed to calculate the mass of a photon, you actually could, thanks to Max Planck and Albert Einstein. There you go. Okay. But why do we care in relation to the atom? Well, Niels Bohr. Thanks, Niels Bohr. Okay. He used light, which is a form of electromagnetic radiation, right? And he used that to figure out that only certain amounts of energy could be absorbed or emitted by electrons. And he figured out that not all electrons use the same amount of energy whenever they absorb and emit energy. It's not always the same quantity. Different electrons in different elements need different amounts of energy to absorb and emit. Okay? So if we flip this over.
I didn't get the last word. What's the last two?
Oh, last two words?
Needed electrons.
Yeah. Okay. So Bohr took that information and he hypothesized that energy absorbed by an electron caused it to be excited. I mean, he couldn't come up with a more scientific word than that, I guess. Right? It excited the electron, just like kids with pixie sticks. And that made it move to an energy level further away from the nucleus. Now, just like kids with pixie sticks, they're not going to stay excited, right? Eventually there's a sugar crash. So eventually that electron is going to return to its original energy level, okay? It's going to have to release that energy. So energy is released by the excited electron. When that happens, it goes back to its ground state. And just so you guys are aware, when that energy is released, it's released as light. It'll give off a photon of light. So it'll absorb the energy, use it to jump up to a new energy level, but then eventually it will emit that same energy. So it'll spit that photon of energy back out as light and go back to its ground state. But different elements, like I said, require different amounts of energy to excite their electrons. So some elements need a lot of energy and some elements only need a little bit of energy. And that's because each element has a different number of protons. Protons are the attractive force holding onto the electrons, right? And every element has a unique number of protons. The energy absorbed or emitted by an electron depends on how many protons are in the nucleus, right? If there's more protons, it's going to need more energy to move away from the nucleus. It also depends on the distance of the electron from the nucleus. So if it's further away, it's not held as tightly by the protons. Just like a kitchen magnet, right? We talked about it last year. If you hold a kitchen magnet up from across your fridge, are you going to feel the attractive force? No. So an electron out in the 7th energy level is probably not feeling that much of the attractive force of the nucleus. However, if it's one of the electrons on that very first energy level close to the nucleus, it's probably going to require a lot of energy to move it away because there's a strong attractive force. It's right there next to the protons. Does that make sense?
So essentially the bigger it is, the less energy it takes. Right? And it would have more electrons.
So it's a function of both. So for bigger elements with more protons, yeah, those first energy level electrons are going to be super hard to remove. But the ones out on the 7th energy level are so far away that they're actually probably easier to remove than some of the first energy level electrons on smaller elements like hydrogen or helium. It's a function of both things. And that function right there, where we take into account the number of protons and the distance from the nucleus, that's called Coulombic attraction. And we're going to talk about that a lot in this unit. It's going to be the answer probably to a lot of short answer questions. And I'm not going to make you calculate Coulombic attraction, and I'm not going to make you calculate the amount of energy it takes to remove an electron. But just in case you ever had to, this equation right here, instead of using wavelength and frequency, Z represents the number of protons, and N down here represents the number for the energy level. So if I needed to know how much energy it takes to excite an electron on the 4th energy level of cobalt, right? Then I would put cobalt's atomic number, its number of protons up here, and I would put the number 4 down here for the energy level. I'd plug that into this equation and I could solve and figure out how much energy it takes to excite an electron on the 4th energy level of cobalt. Okay? But for different elements, can you see how the top number would change? So that amount of energy would be different. And for the energy levels, it would be different, right? So moving an electron from the 4th energy level as opposed to the 1st energy level, even of the same element cobalt, it would be different. You'd be putting different numbers in the equation. Make sense? Okay. All right, so this is the information you guys are going to need to do this worksheet right here. So there's a lot of math on this worksheet. Also, I gave you guys this little thing right here that shows you all the different kinds of electromagnetic radiation. So the high energy stuff is over here, and we did talk about this last year. Low energy is over here. And you've got your little rainbow right here in the middle. So red, orange, yellow, green, blue, indigo, violet. And then do you see how if there's a little bit more energy, it's ultraviolet, right? And if you have less energy than red light, it's infrared. Less energy than that, it's a microwave. Less energy than that, it's a radio wave. The one with the highest energy is gamma rays. Like I said, you don't Hulk out, you just develop tumors. Sucks to be that guy. Okay? Alrighty, let me stop this.